I want you to picture something incredibly mundane, something you've probably seen or done a dozen times, right?
Yeah, just everyday stuff.
Exactly. Imagine you're holding a standard sewing needle. It weighs practically nothing, like what, zero point 0.1 grams of steel?
Barely anything at all.
Right, so you drop it, it falls a few feet, hits your wooden living room floor, and makes that tiny, almost imperceptible little tink sound.
Oh, yeah, I know the exact sound you mean.
So if we were to, slow that down, classical physics tells us a very predictable story. The needle accelerates at 9.8 meters per second squared.
Hmm.
It hits terminal velocity because of air resistance,
Right.
and then, well, upon impact, its tiny bit of kinetic energy turns into acoustic waves.
Right, the sound.
Yeah, and maybe, just maybe, it leaves a microscopic scratch on the varnish. That's the normal world, right? That's Newtonian mechanics playing by the rules.
Very intuitive, very safe.
But today, I want you to imagine that exact same needle, except this time, we are entirely stripping away classical mechanics.
Oh, this is where it gets fun.
It's not falling from your hand anymore. This time, it's traveling at a fraction of the speed of light.
And that is a profound shift in perspective. It really forces us to reevaluate, well, the fundamental building blocks of reality.
Yeah, because it's not just a piece of metal anymore, is it?
Not at all. You take the most harmless object imaginable, you inject it with relativistic speed, and the universe just stops treating it like an arrangement of atoms.
So what does it become?
It essentially becomes an unbounded concentration of pure space-time warping energy.
It's wild. Welcome to the deep dive, everyone. Our overarching topic for this session is exploring the extreme, universe-breaking consequences of a purely relativistic thought experiment.
It's quite a journey we're going on today.
It really is. We're pulling from two phenomenal pieces of speculative astrophysics today. The first is an excerpt from a paper titled The Relativistic Needle and the Solar Torus.
A classic.
And the second is called The Relativistic Needle, a Ladder to Planetary Destruction. So our mission for you on this deep dive is to walk up what the authors call the relativistic ladder.
Step by step.
Exactly. We're going to take this tiny zero point 0.1 gram household object and accelerate it until it has the power to unbind planets, puncture stars, and literally rip localized holes in the fabric of space-time.
And I know this sounds totally like science fiction, right? Like a space opera.
Oh, 100% it does.
But the math we're going to explore today is actually grounded in the established laws of our universe. I mean, the real terrifying laws.
Wait, so this is all theoretically sound?
Yeah, completely. We're simply taking the equations of special relativity, general relativity, and quantum mechanics, and just refusing to flinch when we push the variables to their absolute extremes.
Okay, let's unpack this. To
Right.
understand the destruction we're going to see, we first need to get how the physics of this ladder actually work.
Right, the foundation.
So the sources describe a progression where every rung on this ladder adds another 9 to the percentage of the speed of light.
Usually denoted as C.
Right, so we start at 0.9 C, the 0.99 C, then 0.99 C. And with every single 9 we add, the kinetic energy doesn't just go up a little bit, it scales violently.
To understand why it scales so violently, we have to talk about the language energy. We have to move away from how we normally think about momentum.
Because normally, mass is the big deal, right? Like a bowling ball does more damage than a ping pong ball.
Exactly. In our everyday environment, mass is the dominant character. But as you get close to relativistic speeds, the rest mass of the object, that tiny zero point 0.1 grams, it almost doesn't matter anymore.
It just becomes irrelevant.
Pretty much. Kinetic energy takes over completely. And that energy is governed by something called the Lorentz factor, which physicists write as the Greek letter gamma.
Gamma. So if we're looking at the engine of destruction here, gamma is basically the throttle.
That's a great way to put it. Gamma is the multiplier dictated by special relativity.
How does it work, mathematically speaking?
Well, the formula for kinetic energy at these speeds is essentially gamma minus 1 multiplied by the object's mass and the speed of light squared.
Okay, so E equals mc squared comes into play.
Right. Even for a zero point 0.1 gram needle, its rest mass energy, the energy just locked inside its atoms before it even moves, is roughly 9 times 10 to the 12 joules.
Okay, I want to ground that number for you. That is the energy of a small, localized lightning bolt permanently locked inside a piece of a sewing kit.
Yeah, it's a ton of energy. And as the needle's velocity, or v, approaches the speed of light, c, the denominator in the Lorentz equation, shrinks towards 0.
Meaning gamma gets bigger.
It doesn't just get bigger, it grows without bound. It asymptotes toward infinity. You're taking that baseline lightning bolt and multiplying it by a factor that scales exponentially.
It's kind of like compound interest gone completely rogue, right?
Yes, exactly.
Like a few percent of compound interest over decades balloons a bank account. But gamma compounds over every fraction of a millimeter per second. You push closer to the speed limit. The curve just explodes vertically.
And that vertical curve is why the physics change so radically. You aren't throwing a piece of metal anymore.
What are you throwing then?
The needle stops acting like a solid object. It basically becomes a delivery system for a massive concentration of kinetic energy dumped into a very specific space.
Which brings us to the first massive hurdle, right? The Earth's atmosphere.
Oh, yes. The air.
If we aim this needle at Earth at our first run, 0.9 times the speed of light, my first thought is aerodynamic friction.
Like a meteor burning up.
Yeah, exactly. But at 0.9 C, that's what, 270,000 kilometers per second?
Yeah.
The air molecules can't possibly move out of the way that fast, can they? Does the sky itself become a solid wall?
It becomes far worse than a solid wall, actually.
Really? How so?
Well, in fluid dynamics, air moves out of the way via pressure waves. But those are limited by the speed of sound. At 0.9 C, the needle is moving millions of times faster than sound.
So the air doesn't even know it's coming.
Right. The molecules literally have no physical mechanism to know it's approaching, so they can't be displaced.
So the needle just like bulldozes them into each other.
It forces them to occupy the same quantum space. At 0.9 C, gamma is roughly 2.29. The kinetic energy is now about 2.8 kilotons of TNT.
Wow. 2.8 kilotons. That's like twice the yield of some early nuclear weapons.
Yeah. So as it hits the upper exosphere, it doesn't experience friction. It experiences localized nuclear fusion.
Wait, fusion. It fuses the air.
Yeah. The air molecules are compressed so violently that they fuse. It creates a column of plasma. A bow shock of gamma rays and X-rays blasts out ahead of the needle.
That sounds apocalyptic. Does the needle make it to the ground?
No. By the time it hits 30 kilometers in altitude, the heat and stress completely vaporize the steel.
So the needle itself is utterly destroyed.
The physical object is gone, but remember, conservation of energy is absolute. That 2.8 kilotons of energy is deposited instantly into a sphere of superheated atmospheric plasma.
So it's an air burst.
Exactly. A massive fireball blooms. A blast wave races downward, flattening everything within a 10-kilometer radius and gouging a half-kilometer crater into the crust.
If that happened over a city, the city would just be gone.
Completely erased.
Yeah.
But as the source text dryly points out, on a planetary scale, the Earth barely cares.
It's just a localized catastrophe.
Right.
To really anchor this, the text introduces an observer on Earth. Let's call her Anna. She's a geologist standing in Patagonia on the exact opposite side of the planet from the impact.
Okay, poor Anna. Let's see how she does.
Well, at this first rung, 0.9 C, Anna actually survives. She sees a white flash on the horizon, and about 5 minutes later, she feels the ground shake.
So a scary day, maybe a minor nuclear winter effect globally for a year, but the biosphere adapts.
Right, but we're only on the first rung. The text forces us up the ladder. We have to add nines.
It's clam.
So at 0.99 C, the energy jumps to 13 kilotons. At 0.999 C, it hits 46 kilotons.
Now we're talking about a mountain-sized fireball.
Yeah, and the needle is detonating higher up, at 50 kilometers in altitude. The shockwaves strips forests across a small country. But the atmosphere itself becomes a secondary weapon here.
It does, and it's a fascinating effect. The collision energy shatters the nitrogen and oxygen atoms in the air, creating a lethal cascade of subatomic particles, specifically muons and pions.
I want to pause on that subatomic cascade for a second, because it's a brilliant demonstration of energy turning into mass.
It really is E equals mc squared in action.
It's literally fabricating new exotic particles out of the vacuum energy, right?
Yeah.
It turns the sky into a particle collider.
Precisely. The kinetic energy far exceeds the rest mass of the air molecules. So when the needle slams into a nitrogen nucleus, the energy has to go somewhere. It manifests as new mass.
So it creates pions.
Right, which decay in nanoseconds into muons. And muons are highly penetrating. So while the blast wave is destroying buildings, this invisible shower of muons punches deep into the Earth.
Meaning it delivers lethal radiation to anything organic, even if they're in a bunker.
Exactly. You're shielded from the blast, but the muons still get you.
Okay, here's where it gets really interesting. Our intuition completely fails here. The text pushes us to 8 nines.
Yeah.
0.999999 C.
8 nines, okay. Gamma is now 7,071.
And the kinetic energy is roughly 15 megatons. Now, we just established that at slower speeds, the atmosphere acts like a brick wall and vaporizes the needle.
Right, the plasma airburst.
But at 8 nines, the math says the needle suddenly stops behaving like a meteor and actually survives to hit the ground intact.
It seems like a blatant contradiction, right?
Yeah. If the sky vaporizes it at lower speeds, how does going exponentially faster let it survive?
You'd instinctively think higher velocity means more friction, faster vaporization, but at 8 nines, special relativity introduces kind of a temporal cheat code.
A cheat code.
Yeah. We have to shift our frame of reference. Instead of looking from the Earth, we have to look from the perspective of the moving needle.
Okay, so I'm riding on the needle. What do I see?
From your frame of reference, you're stationary. The Earth is rushing toward you at 8 nines of light speed, and at this velocity, time dilation and length contraction take over.
How extreme are we talking?
Well, for the needle, its internal clock slows down so dramatically that its entire journey through the Earth's atmosphere takes a fraction of a microsecond.
Wow. So if the atmosphere is contracted temporally, what happens to it physically? Spatially.
By Lorentz contraction, the depth of the atmosphere, those hundreds of kilometers of air, is compressed into a thin, ultra-dense fog that's only microns thick.
Microns.
Yeah. So the needle doesn't survive because its steel suddenly got stronger. It hits the ground intact because it literally does not experience enough time for the heat to melt it.
It's exploiting a loophole in space-time. It's like that classic magician's trick, right? The tablecloth and the dishes.
Oh, that's a great analogy.
Yeah, like a slow pull dries the plates off because of friction. But if you pull it fast enough, the inertia of the plates overcomes the friction's time window and the dishes stay still.
Exactly. The needle passes through the sky so fast, the friction just doesn't have the requisite time to dismantle it.
That is wild. So it punches right through the exosphere and the stratosphere.
Before the plasma shock wave can even melt the iron, it impacts the crust directly, carving out a massive crater and delivering 15 megatons deep underground, like a bunker buster.
But the text doesn't let us stay at 8 nines. It actually dials us back down slightly to 6 nines to check in on Anna in Patagonia.
Ah, right. 0.999999 C gamma is 707.
Energy is roughly 1.5 megatons. So we're back to an airburst scenario. What happens to Anna when the needle hits the opposite hemisphere?
At 6 nines, Anna perceives absolutely nothing.
Wait, really? She doesn't even see the flash this time?
No. The energy is deposited so rapidly that the normal delays between light, sound, and seismic waves they become negligible on a human biological timescale.
So it's just too fast for biology.
Exactly. The energy injected into the crust makes the entire planet physically resonate. It rings like a struck bell.
That's a terrifying image.
The flash of gamma radiation, the shock wave, the seismic liquefaction, it all propagates outwards so fast that Anna is biologically erased before her optic nerve can even transmit the signal to her brain.
So her brain never even has the time to register that she saw a flash.
Right. The hemisphere facing the impact turns into an ocean of plasma in a tenth of a second. The far side, where Anna is, lasts exactly 2 seconds longer before the crust liquefies beneath her feet.
2 seconds of borrowed time. I mean, the sheer mechanical transmission of force through a planet in 2 seconds.
Yeah.
It's staggering.
It's a rapid extinction event.
Yeah. We've moved from ruining a city to ruining the biosphere. But the text forces us to keep escalating. We have to transition from extinction to physically unbinding the Earth itself.
This is where we leave biology completely behind.
Let's look at the terrifying jump from 14 nines to 24 nines.
Okay, at 14 nines, the yield is 15,000 megatons. We see regional crust melting, entire ocean basins boil into steam.
Horrific, but still technically a planet.
Right. But at 24 nines, that's 0.999 followed by 21 more nines.
The kinetic energy reaches 6.3 times 10 to the 25th joules, which is, what, a 1.5 billion megaton impact?
Yes.
To give you a sense of scale, the Chicxulub asteroid, the one that killed the dinosaurs, was roughly 100 million megatons. This tiny 0.1 gram needle is hitting 15 times harder than that asteroid.
And the result at 24 nines is the complete end of Earth as a structured planetary body.
It just melts.
Worse, the energy overcomes the latent heat of vaporization for rock. The mantle liquefies and churns outward. The oceans don't just boil, they instantly dissociate into hydrogen and oxygen plasma.
Good Lord.
Yeah, our home planet is reduced to a glowing orange spheroid of magma and vaporized debris. No solid surface at all.
But crucially, it's still a planet, right? I mean, it's a hellish magma ball, but Earth's gravity is still holding that sphere together. The mass hasn't escaped.
That's true, it's still a gravitationally bound system.
Which brings us to the ultimate threshold for this phase, the 39s.
Ah, 39s. This introduces the concept of gravitational binding energy.
Break that down for us. What does that actually mean?
To grasp it, you have to look at gravity as a system of negative energy. A planet forms because mass pulls itself together, settling into the lowest possible energy state.
Okay, makes sense.
The gravitational binding energy is the exact amount of positive energy you'd need to overcome that deficit. It's the energy needed to push every single atom outward so forcefully that gravity can never pull them back together.
It is the mathematical definition of unbinding a world.
Yes, precisely. For Earth, that binding energy debt is roughly 2 times 10 to the 32nd joules.
And to get that from our 0.1 gram needle?
The math demands a Lorentz factor of 2 times 10 to the 19th, which means a velocity with 39s after the decimal.
So when it hits at 39s, what does this unbinding look like? Because blowing up a planet is a huge sci-fi trope. We always see this massive fireball that shatters the world into chunky asteroids. Is that what happens?
The math dictates something far more absolute and honestly less cinematic.
Less cinematic. How?
Well, the kinetic energy is distributed through the planet via a shock wave that moves faster than the speed of sound in the liquid core. Because the energy exceeds the binding energy, every atom is instantly accelerated beyond escape velocity.
So it doesn't crack into big pieces.
No, it's kind of like a spinning carousel, right? Imagine the motor is suddenly cranked so high that the bolts shear off. Every rider is thrown outward in a perfectly straight line, moving too fast to ever curve back.
So the constituent atoms of the Earth are moving away from each other faster than their mutual gravity can break them. They never coalesce again.
Never. The Earth ceases to exist as a mass. It instantly becomes a...
We always think of planets as permanent.
Right, we have this psychological bias. We say things like solid ground. But when subjected to cosmic scales of kinetic energy, planets are actually incredibly delicate.
They're just dust held together by gravity.
Exactly. They're loose collections of debris in a surprisingly weak gravitational embrace. A microscopic object with enough relativistic momentum easily overwhelms that embrace, and the planet just dissolves.
Dissolves into an expanding cloud of dust. So Earth is gone, unbound completely at 39s. But the physicists who wrote this didn't stop there.
Of course not. Why stop at a planet?
Exactly. Dr. Lena Aris, the central figure in the first text, calculates the endpoint of this ladder. Since Earth was vaporized, the experiment demands a vastly more massive target. We have to scale up to the center of our solar system, the Sun.
And the leap in scale here leaves planetary physics entirely in the dust. Dr. Aris calculates what happens at 54 nines of speed.
Let's just break down the sheer, absurd magnitude of the numbers at 54 nines. 0.999, continuing for 54 nines.
The math becomes almost abstract here. The Lorentz factor, gamma, reaches 10 to the 27th. That's a 1 with 27 zeros.
Which means our 0.1 gram needle now possesses 10 to the 40th joules of kinetic energy.
10 to the 40th joule.
We're way past comparisons to nuclear weapons or asteroids. What is the physical analog for 10 to the 40th joules?
The only viable comparison is stellar death. 10 to the 40th joules is roughly 1/10,000th of the total energy output of a supernova.
A supernova.
Yeah. We're taking a measurable fraction of the most violent cosmic explosion in the universe, and we are compressing all of that energy into the exact spatial volume of a sewing needle.
It's not even an object anymore at this point, is it?
Not really. It's a space-time paradox possessing mass.
A paradox hurtling toward the sun. I really want to unpack the journey of this needle through the solar system, because the mechanics of relativity get deeply, wonderfully strange here.
They really do. Let's look at time dilation.
Right. It takes a photon of light, roughly 8 minutes, to cross the distance from where Earth used to be to the sun. But our needle is moving at 54 nines. What does the needle experience temporally?
At 54 nines, time dilation is so extreme that the needle's internal clock is practically frozen relative to the rest of the universe. To a stationary observer, it takes 8 minutes. But in the needle's own frame of reference,
How long does it take?
that entire 150 million kilometer journey happens in 5 times 10 to the negative 23rd seconds.
5 times 10 to the negative 23rd second.
Yeah. A span of time so unimaginably brief that it's actually shorter than the time it takes a photon of light to cross the diameter of a single atomic nucleus.
So for the needle, the journey is functionally instantaneous.
Instantaneous. And because of Lorentz length contraction, the spatial reality warps too. The needle doesn't see the sun as a huge sphere of plasma.
What does it see?
It sees a two-dimensional, infinitely flat pancake of light rushing at it.
Okay, so that's the needle's warped perspective. But what about the sun's perspective? If the sun looks like a pancake to the needle, what does the needle look like to the plasma in the sun's atmosphere?
Well, length contraction applies symmetrically. To the stationary plasma of the sun, the needle's physical length in the direction of its travel is compressed by that same gamma factor of 10 to the 27th.
So how small is it?
It shrinks down to 10 to the negative 27th meters.
Wait, hold on. The diameter of a single proton is roughly 10 to the negative 15th meters. So the needle is vastly, unfathomably smaller than a proton.
Exactly. It's a trillion times smaller than the nucleus of an atom.
If the needle is contracted to a size a trillion times smaller than a proton, how does it physically impact anything? I mean, the outer layer of the sun, the corona,
Yeah,
is incredibly hot plasma, but plasma is mostly empty space on a quantum level.
that's very true.
If you fire something that impossibly small into a field of relatively sparse atoms, wouldn't it just slip right through the gaps? Does this supernova-charged needle just act like a ghost?
Your deduction is spot on. It absolutely acts like a ghost. This all comes down to the phenomenon of quantum cross-sections.
Walk us through that.
In particle physics, the probability of an impact depends on the cross-sectional area of the projectile relative to the density of the target. Because the needle's cross-section is now magnitudes smaller than the wavelength of any thermal photon or atomic nucleus in the corona,
It just misses them.
it physically cannot interact electromagnetically or physically with the plasma. It travels through the 700,000-kilometer depth of the sun's outer layers without disturbing a single electron.
Wow. So it passes through the blazing inferno of a star like it's a perfect vacuum.
Yes, it exploits a loophole in quantum mechanics to ghost right through the star.
But it can't ghost forever, right?
Yeah.
The density of the sun increases exponentially as you move inward. Eventually, this microscopic paradox has to encounter the core. Let's trace it to the exact center of the sun, T-minus 0, the microsecond of impact.
The solar core is an environment of extreme extremes. The density is 150 grams per cubic centimeter. That's about 150 times denser than liquid water.
And the temperature.
15 million Kelvin. In this hyperdense soup of tightly packed hydrogen and helium nuclei, the needle finally exhausts its meme-free path. Its cross-section, however tiny, inevitably intersects directly with a single solitary proton.
One proton. And this is where the classical models and even our advanced quantum models just hit a brick wall.
What's fascinating here is that this specific collision triggers what we call a Planck cascade. Let's look at the center of mass energy of that single proton impact.
Okay, lay the numbers on us.
The needle is injecting its 10 to the 40th joules into the subatomic structure of one nucleus. This equates to 10 to the 36 electron volts of kinetic energy.
And why does that specific energy threshold break the physics engine of the universe?
Because it wildly exceeds the Planck energy. The Planck energy is roughly 1.22 times 10 to the 28th electron volts. It's the absolute theoretical maximum energy limit where our current models of quantum mechanics and general relativity can coexist.
So below the Planck energy, the universe functions normally.
Right. Above it, space and time themselves lose structural cohesion. When the needle hits the proton, it delivers a payload 8 orders of magnitude higher than the Planck limit.
It breaks the speed limit of the universe, and then it shatters the structural limits of spacetime itself.
Exactly. At a normal particle accelerator like CERN, smashing protons creates a beautiful shower of exotic subatomic particles, quarks, bosons, things we can measure.
But not here.
No. Here, the energy density is so severe that it curves spacetime back onto itself infinitely. The collision does not create a shower of particles. It instantly forces the local spacetime to collapse into a singularity.
It punches a localized hole in reality. It makes a microscopic black hole.
A black hole born not from gravity, but from pure kinetic energy. The math Dr. Aris provides for this newly born singularity is incredible. Through the mass energy equivalence of E equals mc squared, the entire 10 to the 40th joules of energy is instantly converted into mass.
So how heavy is this kinetic black hole?
It has a mass of roughly 1.2 1 times 10 to the 23rd kilograms.
To give that a physical analog, that's roughly equivalent to the mass of a small moon.
Yeah.
Or about 1% of the total mass of the Earth we just destroyed.
Yes. And yet, its physical size, its Schwarzschild radius, the boundary of its event horizon, is deeply incongruous with its mass.
Because it's a black hole, it's tiny.
Based on the equations for a non-rotating black hole, a mass of 1.1 times 10 to the 23rd kilograms yields a Schwarzschild radius of exactly 16 centimeters.
16 centimeters. It's the size of a standard basketball.
A basketball-sized sphere of absolute mathematical nothingness, tucked right in the exact center of the sun's core, possessing the mass of a moon.
Okay, but wait. If we have a black hole that's only the size of a basketball, shouldn't it just evaporate? Doesn't Stephen Hawking's theory of Hawking radiation dictate that microscopic black holes leak energy and vanish almost instantly?
That is the exact counterargument any physicist would immediately raise. And the source text actually walks through the mathematics of that tension.
Okay, how does it survive long enough to do damage?
Hawking radiation does cause black holes to evaporate, and the rate of evaporation is inversely proportional to the mass. Smaller black holes bleed energy faster. So we have to calculate the evaporation time against this specific mass.
Walk us through the math on that.
The Hawking evaporation time scales to the cube of the black hole's mass. When you plug 10 to the 23rd kilograms into the equation, the resulting evaporation time is roughly 8.4 times 10 to the 52nd seconds.
8.4 times 10 to the 52nd second. Wait,
Right.
the current age of the universe is roughly 4 times 10 to the 17th seconds.
Correct. The lifespan of this basketball-sized black hole is trillions upon trillions of times longer than the total elapsed time since the Big Bang.
Wow. Okay, so Hawking radiation is entirely negligible here.
Completely. The singularity is remarkably stable. And more critically, because it's located in the most densely packed environment in the solar system, it's continuously fed.
It begins to eat the sun from the inside out.
Immediately. We map this consumption using Bondi accretion. The Bondi accretion formula calculates the rate at which a black hole draws in surrounding gas based on density and pressure.
And the core is under massive pressure.
Immense hydrostatic pressure. The plasma is aggressively forced across the event horizon. The math yields a staggering accretion rate. The black hole consumes 6.7 times 10 to the 14th kilograms of solar mass every single second.
That is the equivalent of Mount Everest falling into a basketball hoop every single second.
And at that exponential rate, the black hole will double its mass in less than 5 years. Within a few decades, it'll comfortably consume the entire solar core.
Okay, so we've established we have this parasitic basketball-sized black hole silently devouring the sun's core. But the overarching promise of Dr. Aris's thought experiment was that the sun turns into a torus, a donut.
Ah, yes, the donut.
If the black hole is just slowly eating the core over decades, how do we get from a tiny parasite to a massive, glowing solar donut?
The formation of the solar torus is a profoundly violent, transient event that occurs right in the immediate aftermath of the impact, long before the black hole consumes the star. We have to rewind the clock.
Back to the microsecond of impact.
Right. The creation of the black hole only accounted for the conservation of the needle's kinetic energy. It did not account for the thermal shock wave.
Right. Because when the needle hit the proton, it didn't just vanish into a singularity, it dumped an apocalyptic amount of thermal energy into the surrounding plasma at the same time.
Exactly. Let's trace the chronological sequence of the torus forming, starting at t plus 0.1 seconds after impact.
1/10 of a second. What happens?
The thermal shock wave instantly spikes the temperature of the surrounding solar core from 15 million Kelvin to over 100 billion Kelvin.
100 billion.
Yes. And at 100 billion Kelvin, the physics of the plasma undergo a radical phase shift. The thermal photons of light suddenly possess so much energy that they spontaneously undergo pair production.
Wait, what does that mean?
They convert themselves into pairs of matter and antimatter, specifically electrons and positrons. The entire core of the sun flashes into a roiling, opaque fireball of gamma radiation and annihilating antimatter.
Which produces an unimaginably powerful outward pressure, I'm assuming.
Massive radiation pressure. Let's move to t plus 1 second to t plus 10 seconds.
Okay, 1 to 10 seconds.
The radiation pressure generated by this antimatter fireball completely overwhelms the inward pull of the sun's gravity. The hydrostatic equilibrium that keeps the star stable is shattered.
So the star is blowing itself apart.
The inner 10% of the sun's mass begins to accelerate outward at a significant fraction of light speed. And here is the critical geometric detail. The black hole at the center is still only the size of a basketball.
Right, so it's way too physically small to block the explosion.
Exactly. It cannot obstruct the expanding sphere of superheated core material. So this relativistic shockwave simply punches right through the overlying cooler layers of the sun's radiative and convective zones.
It's essentially a directional shaped charge going off inside a giant sphere of fluid.
That's a perfect way to visualize it, which brings us to T plus 30 minutes.
30 minutes, what do we see?
At 30 minutes, the expanding shockwave finally breaches the surface of the sun, the photosphere. If you were observing this from a safe vantage point in deep space, the visual would be staggering.
Paint the picture for us.
The blinding, uniform surface of the sun would violently rupture. The overlying layers of plasma are pushed radically outward and upward along the path of least resistance. Meanwhile, a central cavity is blown completely clear.
A literal dark hole appears right in the center of the star.
Yes. The plasma is forced into a ring geometry. For a fleeting window of just a few hours, the sun ceases to be a sphere. It forms a brilliant, glowing torus of superheated plasma hundreds of thousands of kilometers across.
With an absolute void of darkness right in the middle where the black hole is sitting at the bottom of the cavity, it is a genuine, glowing solar donut.
It really is.
The physics governing that shape seem like such a delicate, paradoxical balance. It's this razor-edge race between the apocalyptic outward blast of the thermal shockwave and the relentless, creeping inward pull of the growing black hole.
It's an architecture of pure chaos. It accidentally forms something structurally beautiful, but it just can't last.
Because the black hole is getting bigger.
Right. It is entirely transient. By T plus 1 hour, the outward momentum of the torus's inner edge is depleted. The black hole, having grown exponentially through accretion during this chaotic hour, heavily asserts its gravity.
So it pulls the donut back in.
Violently. It pulls the inner edge of the plasma torus back inward. But simultaneously, the outer edge of the torus is still coasting outward on the blast wave.
The differential in velocities just shears the perfect torus apart.
Yes. The geometry collapses into an asymmetric, turbulent mess.
And by T plus 1 day?
By T plus 1 day, the torus is completely erased, the evacuated cavity is gone, the star has collapsed back in on itself, but it's no longer a stable star.
What is it now?
It's become a violently rotating, rapidly infalling accretion disk of plasma, screaming as it spirals toward the event horizon, emitting jets of hard X-rays and gamma rays far deadlier than the gentle solar wind we once relied on.
Which brings us to the final act of this analysis, the aftermath, the wounded star. The torus has collapsed into a churning accretion disk. We need to examine the long-term reality for the rest of the solar system.
Because the implications here definitely defy common science fiction tropes.
Exactly. What we have mathematically modeled is fundamentally a failed supernova, right?
Yes. In standard astrophysics, a supernova generates enough outward radiation pressure to completely unbind the star's outer envelope. It blows it off into the interstellar medium, leaving behind a naked neutron star or black hole.
But here,
the energy injection, while immense, just wasn't sufficient to overcome the gravitational binding energy of the entire solar mass.
so the bulk of the star is still trapped in the gravity well.
Yes. The remaining 99% of the sun's mass is now in a state of chaotic freefall toward the central black hole. As this massive volume of gas spirals inward, atomic friction heats the material to millions of degrees.
And that generates the relativistic polar jets you mentioned.
Right. Beams of ionized matter shooting outward at near light speed. It bathes the solar system in an agonizing, continuous glow of extreme ultraviolet and X-ray radiation.
If those polar jets happen to align with the orbital plane of any planets.
They would systematically sterilize all complex chemistry within hundreds of light years.
But let's assume the jets are aligned perpendicular to the ecliptic plane. Let's assume the planets, like perhaps a surviving Mars or a frozen Earth, if we ignore our previous 39 unbinding experiment.
Let's assume they survive the initial burst.
Right. If the sun is gone, functionally replaced by a black hole, what happens to planetary orbital mechanics? Does the solar system just, fly apart into deep space?
Yet this raises an important question, and it touches on one of the most pervasive misunderstandings regarding general relativity and black holes.
A lot of people think black holes just suck everything in.
Exactly. But a black hole is not a cosmic vacuum cleaner with infinite reach. Its gravitational influence is strictly dictated by its mass.
Okay, so let's look at the mass budget.
We must account for the mass budget of this system. The black hole was formed entirely from the mass of the sun. The needle's added mass was negligible. Therefore, the central mass of the solar system has not changed.
It is still exactly one solar mass.
Exactly one. It's just compressed into a much smaller, denser volume, which means its gravitational footprint at a distance is identical.
So according to Newton and Einstein, if you replace the sun with a black hole of the exact same mass, the curvature of space-time at the distance of the planetary orbits remains completely unaltered.
The gravitational field does not change by a single fraction of a percent.
So the profoundly terrifying reality for a surviving planet is that the orbital mechanics continue flawlessly. Earth continues to trace its exact elliptical path, completing a revolution every 365 days.
The planetary clockwork ticks on perfectly.
But the energy dynamic is completely severed. There is no visible light, and there is no heat.
The solar system is plunged into absolute eternal darkness. And the thermodynamic consequences for a terrestrial planet are rapid and catastrophic.
Because without the constant influx of solar radiation, the surface temperature just plummets.
Rapidly. Within weeks, the oceans freeze entirely, from the surface all the way down to the abyssal plains. They transform into rigid mountains of dense, expanding ice.
And the atmosphere.
As the temperature crashes toward absolute zero, the atmosphere itself loses the kinetic energy required to remain a gas. The nitrogen and oxygen literally condense out of the sky.
Oh, wow.
They fall to the barren surface as a continuous silent blanket of cryogenic snow.
A frozen, dead rock, locked in an inescapable orbit around a ghost.
A ghost indeed.
The visual finale painted by the physics here is deeply haunting. If you were standing on that frozen, nitrogen, snow-covered crust, looking back at the center of the solar system where the sun used to burn, you wouldn't see the chaotic beauty of the torus.
No, the torus is long gone.
You wouldn't see light. You would just see a black void, silhouetted faintly against the dusty, glowing band of the Milky Way.
Just a silhouette.
The only physical evidence that the anchor of our solar system still existed would be a microscopic, shimmering ring of distant starlight, bending and warping around the event horizon due to gravitational lensing. A silent, invisible grave where a star once existed.
It is the ultimate cold equilibrium. It is the mathematical certainty of what happens when you introduce an unbounded amount of kinetic energy into a delicately balanced, gravitationally bound system.
It tries to process it and fails.
The system attempts to process the energy, fails, and collapses into the lowest possible thermodynamic state.
Okay, let's pull back and synthesize the journey we just mapped out. We started with a harmless 0.1 gram sewing needle. By strictly adhering to the equations of relativity, we accelerated it up the ladder.
We certainly did.
We watched it weaponize the atmosphere and shatter the Earth's crust at a fraction of light speed. We pushed it to 39s, overcoming the planet's gravitational binding energy, scattering the Earth as a diffuse plasma cloud.
Across the inner solar system, yeah.
And finally, we aimed it at the sun, pushed it to 54 nines, and injected so much kinetic energy into a single proton that it collapsed the local spacetime, tearing a basketball-sized hole in reality that briefly turned our star into a glowing plasma torus.
Before leaving behind a dead, frozen, and dark solar system. The entire exercise serves as a profound testament to the elegant brutality of physics.
So what does this all mean? Why walk through this specific thought experiment? What is the practical takeaway from exploring such absurd extremes?
Well, I think it demonstrates that in the architecture of the universe, speed and kinetic energy hold the ultimate trump card over mere mass and size.
Right. A grain of sand or a sewing needle can literally murder a star, provided it is moving fast enough to bend the rules of spacetime.
Which perfectly sets up the final unresolved dialogue in Dr. Eris's story.
Oh, right. The ending.
After mapping out this entire catastrophic timeline on a whiteboard, her colleague, visibly disturbed by the math, asks the only rational question left. He asks, can anyone actually build a needle that fast?
And Dr. Eris simply replies, not yet.
Not yet. That is the specific implication I want you to sit with today. In modern astrophysics, we observe millions of stellar mass black holes scattered across the Milky Way and beyond.
And our standard models assume they're just natural.
Right. We assume they are the natural, inevitable end states of massive stars collapsing under their own weight. But if there are civilizations out there capable of godlike engineering,
Civilizations that understand how to accelerate a microscopic projectile to 54 nines.
exactly, how would our telescopes ever know the difference?
We wouldn't. The resulting black hole looks mathematically identical.
Exactly identical. It forces you to look up at the night sky and ask a deeply unsettling question. Are the silent, invisible black holes we observe natural phenomena, the quiet graves of exhausted stars? Or are we staring blindly into a dark forest of a universe, looking at the cosmic crime scenes of an ancient, hyper-advanced war where stars are systematically snuffed out by invisible relativistic bullets?
That is a chilling paradigm shift to mull over. From a tiny needle dropping on a wooden floor to the realization that the physics of the universe actively allow for the silent murder of stars.
It really reframes everything.
Thank you for walking up the relativistic ladder with us today and braving the extreme edges of astrophysics. Until our next deep dive, keep questioning the mechanics of the universe around you.